So previously, we were looking at the normal curve. And the normal curve was one with a mean of 0 and a standard deviation of 1. Really easy to draw and so forth. But what if we have a different mean and a different standard deviation? So let's kind of talk about that. We have a study reported that the length of pregnancy for conception to birth is approximately normally distributed. Okay, it's going to look like that bell curve. And it has a mean of 272 days and a standard deviation of 9. So let's think about what that would look like. So here's the curve. And right in the middle, that's my mean. That's my mean. That's 272 days. Now, we normally count out 3 directions each way when we draw our curve. 1, 2, 3, 1, 2, 3. And I'm adding my standard deviation going this way and subtracting it going that way. So 272 plus 9 would give me 281. Sorry about that smear. Then add 9, I get to 290. Add 9, 299. Subtract it. So if I subtract 9, I'm going to be at 263. And then subtract 9, I'm at 254. And then subtract 9, I'm at 245. So here's our layout. And we want to know what proportion of pregnancies last less than 259 days. Well, let's think about where that would be. 259 would be approximately in between here and here. So we're talking about somewhere like here, and less than that would be to the left. Longer than 280. Well, this is 281, so 280 is going to be over there. So we're talking about somewhere in this range. A pregnancy is considered full term if it lasts between 252 and 298. That's a lot. So that's going to be, whoa, 252 would have been about here, and 298 would be almost at the other end. This is going to be a very high proportion. Now let's review how to calculate it. Well, the best way is to use our NumWorks app. So again, we're going to go in and we're going to choose the inference probability, and we're on a normal curve. Now, before we were just using a mean of 0 and a standard deviation of 1, but we can put in anything we want. So the mean here was 272, and the standard deviation was 9. And it draws our picture. Now, the first one we wanted was less than 259 days. So we get 0.074. It's a really low percentage. Longer than 280. So wait, I should have, this is probability that X is less than 259. This would be the probability that X is longer than 280, so greater than 280. Now remember, with these, the or equals to doesn't matter because these are continuous. So greater than 280 is 0.187. Pregnancy is considered full term if it's between 252 and 298. So we're going to be going between those. $252 and $298. Whoops. It's fun. And I get 0.985. I knew that was going to be a big percentage. Big proportion, big probability of your pregnancy lasting full term. General Electric manufactures a decorative crystal clear 60-watt light bulb that is advertised will last 1,500 hours. Suppose that the lifetimes of the light bulbs are approximately normally distributed with a mean of 1,550 and a standard deviation of 57. What probability of the light bulbs will last less than the advertised time? So X is less than 1,500. So I need to change my mean. What was the mean? The mean was 1,550. And the standard deviation was 57. And we want to know what probability of having a light bulb that lasts less than the advertised value. And I get 0.19. What's the probability that it will last more than 1,650 hours? The probability that X is greater than 1,650. So greater than 1,650. Ooh, that's a very small chance. It's 0.0397. What is the probability that it'll last between 1625 and 1725? Notice that's above the mean. So we're talking about a light bulb lasting a very long time. We want between said 1625 and 1725. And notice that's actually a small percentage too. It's 0.093. What is the probability that a randomly selected light bulb will last longer than 1,400 hours? Now, what do you think about that one? Is that going to be a big probability or a small one? So think about where that would lie. So 1,400 is right here. And if we're greater than that, that should be a pretty high probability. Because 1,400 is less than the mean. And it is 0.996. That's awesome. Now, the next one we haven't really talked about how to do yet, but it's really not that hard. How long will a light bulb last if it is in the top 15%? So let's think about what that would mean. So if I'm thinking about that curve, top 15% would mean that it's in the top and top 15%. So we're talking about this being 15% or 0.15. So we're trying to find the X value that gives me a probability on that right edge of 0.15. So let me show you how we can do that. We are already on a greater than, right? And I want to figure out where this boundary line needs to go so that the probability is 0.15, 15%. So on the NumWorks app, it's really nice. I can go over here and change that probability to 0.15 and watch what it's going to do. It's going to move that boundary to show me what line, what value gives me an area of 0.15, a probability of 0.15. So 1609. What is the length of a time a light bulb lasts if it is at the 8th percentile? Now remember, 8th percentile would be in the bottom 8. 8th percentile would be 8% in the bottom. So that would be a 0.08 in the bottom. So I would go to a less than.
Good morning.
We want to know what value is going to give me a probability of 0.08. And that's 1469.9. That would round up to 1470. So we're going to continue that with finding some more values from their proportions and probabilities. So this is really awesome. So Mensa is an organization whose membership is limited to people whose IQ is in the top 2%. And assume that scores on an IQ test are normally distributed with a mean of 100 and a standard deviation of 15. Top 2% would be here, 2%, whoops, 2% or 0.02. So we need to know what that cutoff line is to be in the top 2%. Whoops. So I have to go back and change my mean to be 100 and standard deviation of 15. And we want to be in the top 2%. So I need to be on the right side. And we want to know what value is going to give me a probability to the right of 0.02. And it gives me 130.8. Suppose that the blood pressure of men aged 18 to 29 have a normal distribution with a mean of 120 and a standard deviation of 10. What value of blood pressure is the 75th percentile? So 75th percentile means that it's 75% below it and 25% above. So you have two ways to do it. You could either do a less than at 0.75 or greater than at 0.25. I'm going to do a less than at 0.75. So I need to change my mean to 120 and standard deviation to 10. And we have a less than, and we want to know what value would make it be at 75%. That's 126.7. A pediatrician obtains the heights of her 200 3-year-old female patients. The heights are approximately normally distributed with a mean of 38.72 and a standard deviation of 3.17. The pediatrician wishes to determine the heights that separate the middle 98 of the distribution from the bottom 1% and the top 1%. So on our calculator, it is nice because we do have that option of doing the between. And we want this middle to be a 98%. So we need to change our mean to be the 38.72. And the standard deviation was 3.17. And I want the middle to be 0.98. And it gives me my range. It gives me my lower value and my upper value. So it's saying it's from 31.3 to 46 point, basically 09 inches. Last example. Suppose that men's foot lengths are normally distributed with a mean of 25 and a standard deviation of 4, and women's foot lengths are normally distributed with a mean of 19 and a standard deviation of 3. Sketch both curves on the same axis. Okay, so we've got a mean of 25 and a mean of 19. So let's see, let's make that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 25, 30, 35, 40, and so forth. Okay, so mean of 25 for the men with a standard deviation of 4. So mean of 25 means that the men are starting right here. So this would be, let's do 2 different colors. Let's do the men's in red. So mean is right there. And so their standard deviation is 4. So 1, 2, 3, 4, I'm at 29. So here's 25. 1, 2, so 1, 2, 3, 4. This is at 33. 1, 2, 3, 4. That's at 37. I gotta go backwards also. 1, 2, 3, 4. That's at 21. 1, 2, 3, 4. I'm at, what is that? 17. 1, 2, 3, 4. That's at 13. So my high point for the men is going to be here, and it's going to trail off either way. So here and there. Okay, so there's the men. Now let's look at the women's foot lengths. Okay, so women's, we're going to do, let's do pink. Okay. Oh, pink is too close. Let's do a blue then. Blue. All right, they have a mean of 19. Mean of 19. And their standard deviation is 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So their high point is going to be here, and it's going to be a little narrower. Why is it a little narrower? Well, their standard deviation was smaller. Okay, so the women had a mean of 19 and a standard deviation of 3. And the men had a mean of 25 and a standard deviation of 4. What is the probability a man's foot is smaller than 22 centimeters? So the probability that the man's foot is smaller than 22. So since it's the men, I need to change this to be 25 and 4. And we want smaller than 22. The probability is 0.227. And the probability that the woman's foot is greater than 22, I would need to change my mean and standard deviation, 19 and 3. And we want greater than 22. And it's 0.159. And let's look at that boundary at 22. That's right here. So notice that the tail for the women is smaller than that tail for the men. So that does make sense. What size foot would a man in the upper 5% of all men have? So here's the men's upper 5% would be up here, 0.05. I'm going to go back, change my mean and my standard deviation, and I want the upper 5%. So when we got the percentage, the probability, I'm going to put that in on the equals to side, and it's going to give me my boundary there, 31.6. What size foot would a woman in the bottom 10% have? So bottom 10% would be down here. So I need to change it back, 19 3, bottom 10%, 15.16.